Hi, I'm Young Kim, and I'm gonna talk about a paper, Bias Swap, Removing Dataset Bias with Bias Taylor Swapping Augmentation. This work has been jointly done by Jihyun Lee and Jaegol Chu at KAIST. Imagine the training of a neural network which classifies whether the object is camel, and assume that most of the camels are taken in deserts. After training, we evaluate our model on the test images where the camel is standing on the desert. And it is obvious that our classifier will achieve the satisfactory accuracy. However, what if we have the camel test images, which are taken not in the desert, but in other places such as park? Our classifier may completely fail to generalize its ability to such camel image. The reason behind such failure is the bias dataset. There are too many camels in desert than those in other areas, and the classifier would heavily rely on the desert rather than the camel itself. Therefore, desert works as a bias attribute when training a camel classifier. And the classifier trained on the bias dataset does not generalize to the unbiased test dataset, which have different distribution. In this work, our main goal is to remove such dataset bias via providing additional augmented images during training. Throughout the paper, we utilize the synthetic as well as the real-world dataset, which have correlation between the bias and the class labels. The images which contain such correlation are defined as bias guiding images, while those having no correlation are bias contrary images. So, the first step of our proposed method is a pseudo-bias label assignment. First of all, motivated by the observation in NAM, we train a biased classifier by utilizing the general concept of bias as easy to learn via generalized cross-entropy laws. Then, we assume such a classifier would classify a bias guiding image correctly with high confidence. On the other hand, it would classify a bias contrary image incorrectly with high confidence or low confidence. Based on such assumption, we define a bias score which measures how aligned the image is toward the bias. Then, we can assign each image the bias guiding or bias contrary label according to the empirically determined threshold. Next, we train our bias tailored swapping augmentation network. We first provide the bias guiding and contrary images separately to each encoder branch using pseudo-bias labels. At the same time, in our proposed CAM-based patch sampler, we integrate the class activation map of the bias classifier to the style sampling module, which enables to primarily sample the bias relevant regions during image translation. Given such sampled patches, the bias tailored patch discriminator encourages the styles of synthesized image to be similar to those of bias contrary image. At the same time, the features other than the bias are provided from the bias guiding image, leading the synthesized image to maintain the bias irrelevant attributes of bias guiding one. By adding such augmented image into our training dataset, we can alleviate the dataset bias caused by the dominant number of bias guiding images in the dataset, thus enabling the model to learn the bias representation. As a result, the table demonstrates that our method achieves the robust classification results in both biased and unbiased test accuracy against the baseline methods over every dataset. As shown in the qualitative result, the generated images contain the bias attributes extracted from the bias contrary images while maintaining the bias irrelevant attributes from the bias guiding images. For example, a young female in the first column translated into a young male in the third column by reflecting the gender attribute from a young male in the second column, while retaining the bias irrelevant aspects such as wearing sunglasses and smiling. This is the end of my presentation, and thank you very much for watching this video. For more detailed information of our paper, please visit our poster presentation scheduled in session 11A and B. Thank you.